Hi guys, today we're going to take a look at question 3 of the 2017 exam, paper 2. Okay, so ABC is a triangle where the coordinates A and C are 0, 6 and 4, 2 respectively, as we can see on the diagram. And 2/3, 4/3 is the centroid of the triangle ABC. AG intersects BC at the point P. So if we extend this line AG, then it will hit BC at P, and the ratio of AG to GP, so this length to this length, is 2 to 1. Okay, so we want to find the coordinates of P. Okay, so we know that the ratio from A to G, the length of A to G to the length of G to P, is 2 to 1. Or in other words, G divides AP in the ratio 2 to 1. Okay, and then we have a formula for a point dividing a line segment in a given ratio. So we know that the point dividing PQ, just any two lines, in the ratio A to B can be written as B times x1 plus A times x2 all over B plus A, and then B times y1 plus A times y2 all over B plus A again, where P, the first point, is x1, y1, and Q, the second point, is x2, y2. Okay, so we know that, so let's say if we take our 3 points, A, G, and P. Well, then G divides AP in the ratio 2 to 1. So A equals 0, 6. P equals, well, that's our second point, our Q, x2, y2, and G equals the point that divides them, 2/3, 4/3, and A equals 2 and B equals 1. So B1 times x1, 0, plus A2 times x2 all over B plus A, which is 3, is equal to, using this formula, B times y1, so 6, 1 times 6, plus A times y2, plus 2y2, is over B plus A, 3. So this is the point that divides A and P into the ratio 2 to 1. But we know that this is just G, which is 2/3 2/3, 4/3. So we can let this equal 2/3. So 2x2 equals 2. So x2 equals 1. And then the y-coordinate equals the y-coordinate. So 6 plus 2y2 equals 4. Let the numerator equal the numerator. And so then 2y2 equals minus 2. So y2 equals minus 1. So p is equal to 1 minus 1. Okay, so now we want to find the coordinates of B. Okay, so what is B? Well, we know that the centroid of ABC, this triangle, we know that that centroid is G, which is 2/3, 4/3. Okay, so, and we have a formula for the centroid of a triangle. It is x1 plus x2 plus x3, so the 3x coordinates over 3, the average of the 3x coordinates, and then the average of the 3 y coordinates. Okay, so our x coordinates, our 3 sets of coordinates are A, which is 0, 6, B, which is unknown, let's call this xy, and C, which is 4, 2. Okay, so if we put this into our formula and then try to solve for y and x, solve for x and y, so the average of the x coordinates, 0 plus x plus 4 over 3, and the average of the y coordinates, 6 plus y plus 2 over 3, is equal to our centroid, which we know is 2 over 3, 4 over 3. Okay, so now we just have to look at the denominator. So 0 plus x plus 4 equals 2. So x equals minus 2. And 6 plus y plus 2 equals 4. So y equals minus 4. So b equals minus 2 minus 4. Now prove that C is the orthocenter of ABC. Okay, so what is the orthocenter? First of all, the orthocenter is the intersection of the altitudes of a triangle. And that begs the question, well, what are the altitudes? So the altitudes of a triangle are the, let's say if we have a triangle ABC, which we do, then one altitude would be the perpendicular line, so it's perpendicular to BC through A. Another one would be the line that is perpendicular to AB through C. And the other altitude would be the line that is perpendicular to AC, which goes through B. So the intersection of these three lines is what we call the orthocenter. And so C would be the orthocenter if the line, so there's this, we have this little trick. So the orthocenter is a vertex if the triangle has a right angle. And the orthocenter is then on the vertex with the right angle. If the triangle has a right angle. And what do I mean by that? So the orthocenter of A, B, and C will be C if and only if this is a right angle. So if BC and AC, if they're perpendicular to each other. So in general, so this is just true in general. So if the orthocenter, okay, so if the triangle has an obtuse angle, so the one of the angles is greater than 90, has an obtuse angle, then the orthocenter is outside the triangle. Is outside. If the triangle has all acute angles, if the triangle, so if all angles are less than 90, is acute, then the orthocenter is inside. And if one of the angles is 90, so it's not obtuse but it's not acute, then the orthocenter is one of the vertices, one of the points ABC. So now what it is we're looking for, we want to show that the triangle has a right angle at C, and then the orthocenter will be C, is the vertex C. Okay, so does ABC have a right angle at C? Okay, well, let's think about what would it take for this to be a right angle. Well, if this was a right angle, as we talked about, then these two lines, BC and AB, would be perpendicular. So are AC and BC perpendicular? And we know that two lines are perpendicular if their slopes multiply to -1. So do MAB times, MAC, not MAB, the slope of the line AC times the slope of the line BC, do they equal -1? And so if they equal -1, then the lines are perpendicular, and that means ABC has a right angle at C. And if ABC has a right angle at C, then the orthocenter is C. So there's kind of we're actually proving something like 4 steps away, but they all mean the same thing. Okay, so well, let's look for the slope M of AC. Well, we can use our slope formula. The slope of the line between 2 points is y2 minus y1 over x2 minus x1. Okay, so the slope of AC will be, let's let let's let A be x1, y1. And let's let C be x2, y2. Then the slope is 2 minus 6 y2 minus y1 over 4 minus 0, which is just minus 1. So the slope of AC is minus 1. And now let's look at the slope of BC. Again, using our slope formula, this time let's let B, which is minus 2 minus 4, let's let this be x1, y1. And again, let's let C for 2 be x2, y2. Then our slope, MBC, is 2 minus 4 over 4 minus 2. So this equals 1. So the slope of AC, minus 1, times the slope of BC, so this equals minus 1 by 1, which equals minus 1. So AC and BC are perpendicular. And because AC and BC are perpendicular, then the triangle ABC has this right angle here, a right angle at C. And since ABC has a right angle at C, then its orthocenter is C. Now it's a little, this is a tricky question. Showing that something is the orthocenter is not easy. You could construct the altitudes yourself, which would be a bit of a pain, but you could construct them and then find their intersection. But I do think, and show that that intersection is C, but I think that understanding what the orthocenter really means, where is the orthocenter given a triangle? If it's an obtuse triangle, then the orthocenter is outside. If it's a acute triangle, then the orthocenter is inside. And if it's a right angle triangle, then the orthocenter is on the right angle vertex. So having that understanding of what the orthocenter is will make this question a lot easier. But you can just knowing that the orthocenter is the intersection of altitudes and knowing what the altitudes are, that would be enough to get this question. It would just take a little bit longer.